Now you are going to learn about the last characteristics, static characteristics of the transistor. The last characteristics is called output characteristics of the transistor. Already you have learnt about the two characteristics. One is transfer characteristics of the transistor and input characteristics of the transistor. Now we are going to learn about the output characteristics of the transistor. Now look at the circuit. Already I have explained about the circuit. The same circuit was used to find out the input impedance of the transistor and current gain of the transistor. The same circuit to be used for finding the output impedance from output characteristics. Output impedance is one of the important parameter of the transistor. Output impedance is the one of the important parameter of the transistor. To find out the output impedance of the transistor, we need a tabular column and we have to draw the graph also. The graph which is drawn there is called as output characteristics curves. Okay. Here I will explain how to perform the experiment. Here the thing is IB, the base current, input current IB is there, no, that should be kept constant. By adjusting the rheostat RH1, we have to fix the value of, we have to set the value of IB as 0. IB value must be kept at 0 microampere here. Is it clear? In IB, the value of IB must be set as 0 with the help of the rheostat RH1. Are you clear? So by keeping IB as constant 0 microampere, we have to vary the VCE. What is VCE? Voltage across collector and emitter must be varied. How to vary the VCE? VCE can be varied by adjusting the rheostat RH2. By adjusting the RH2, the voltage across collector and emitter can be varied. Are you clear? If you vary the VCE, that could be monitored in the voltmeter. So you have to vary the value of VCE. So first you have to keep 0.1 volt. The corresponding variation in the collector current in the milliammeter must be noted. Let us imagine for 0.1 volt VCE, the corresponding collector current is 0.3. Are you clear? So by the time which one should be kept constant? IB must be kept constant. Again by adjusting the rheostat RH2, vary the value of VCE as 0.2 volt. Note down the corresponding reading in the collector current. Are you clear? In the milliammeter. Are you clear? Let us imagine the collector current value is 0.7. Vary the value of the VCE from 0.2 to 0.3. The corresponding variation in the collector current to be noted. Let us imagine 1.5. So after varying the VCE, you will get the corresponding variation in the collector current. After attaining a particular value, the IC value, that one will attain a saturation value. Are you clear? Constant value it will be attained. Are you clear? So note down the reading. Here space is not sufficient, that's why I have stopped up to 0.5 volt. That should be taken up to 1 volt. 0.5, 0.6, 0.7, 0.8, 0.9 up to 1 volt. The reading must be taken. Only then you are able to draw a curve. Are you clear? So for this particular IB value 0 microampere, this part of the graph is drawn. Are you clear? Look at the graph here. The graph what is drawn here is drawn for IB is equal to 0 microampere. Are you clear? Now this is the first graph, first curve which is obtained in the output characteristics by the time IB value is 0 microampere. Now what we have to do? By adjusting the rheostat RH1, we have to vary the value of IB. The next IB value is 20 microampere. Is it clear? Previously that one was 0 microampere. Now the IB value is changed from 0 to 20 microampere. Again we have to do the same procedure. VCE to be set with the help of RH2, VCE value to be varied, the corresponding IC value to be noted down. After getting a set of value, we can draw the next curve, that is for 20 microampere. This is a graph drawn for IB is equal to 20 microampere. Are you clear? Again, the base current to be varied, that is from 20 microampere to 40 microampere. We have to vary the value of VCE, the corresponding IC to be noted down. Again a set of value you will get, the set of reading to be used for drawing the graph, this one IB is equal to 40 microampere. The third curve that can be obtained from the third set of readings. So like that the table to be extended for 60 microampere, 80 microampere and for each set of IB values, you can draw the curve like this. Are you clear? So right from IB is equal to 0 microampere up to even you can go up to 100 microampere. So you will get a set of curve. The set of curve drawn is called as what is this? Output characteristics. There in x-axis VCE is taken and in y-axis IC is taken. Are you clear? And VCE is measured in volt, IC is measured in milliampere, and here the graphs curves are drawn for different values of IB. All IB values are measured in terms of microamperes. Are you clear? So this nature of characteristics curves are called output characteristics curve. Are you clear? Now, what is the purpose of drawing the graph? From this graph, we are able to measure the third parameter called output impedance. Are you clear? Now, how to get the value? Here, you have to draw the slope. Are you clear? You can draw a slope here. From the slope, you are able to get the output impedance. Are you clear? Now, extend the line from y-axis. This one that gives you the difference in IC. Are you clear? And the corresponding change in the VCE can be measured. That part of the portion, that one gives you del VCE, difference in VCE you will get. So with the help of del IC and del VCE, we are able to get the output impedance. Are you clear? Again, to calculate the output impedance, we have to use the Ohm's law. V is equal to I into R. That is a fundamental formula from Ohm's law. Here, what is required? That impedance is required, output impedance is required. Again, I will write it like this. V is equal to I into, instead of capital R, there you write it as RO. RO is a symbol for output impedance. Impedance is a kind of resistance offered in the output part of the circuit. To the flow of IC, some amount of resistance is offered in the output region, that is called output impedance. Are you clear? So, how to write the formula? Output impedance RO is equal to V divided by I. Now, since all are related with output, which one is the output voltage? Voltage across collector and emitter is the output voltage. Therefore, we have to write it as VCE. There we have to find out the change in value. Therefore, del symbol must be written. What is the respective corresponding current, collector current? Therefore, IC must be written in the output. The corresponding variation in the collector current must be measured. That's why I have written the del symbol. Change in collector current, change in collector emitter voltage. This is the formula to calculate the output impedance. Are you clear? Now, RO is a symbol for, what is this? Output impedance. Output impedance. That is one of the important parameter of the transistor. Are you clear? Now we have to draw the bracket. When these two are changing and observed, which one is kept constant? IB is kept constant. The value IB that must be written outside the bracket. Are you clear? Since it is kept constant, the IB must be written outside the bracket. Now we have to define what is output impedance. How to define output impedance? I will tell you the definition. The same thing may be asked in the examination also, 2 mark. Output impedance of the NPN transistor in common emitter mode is defined as the ratio of change in collector emitter voltage to the change in collector current at constant base current. That is the definition for output impedance. Since it is impedance, the impedance value must be measured in ohm. Usually RO value will be very low. RO value will be very low. Are you clear? So this is the complete experimental and theoretical part of the output characteristics, may be asked in the 3 mark also. Okay. Now we are going to learn, there are several regions are observed in the case of output characteristics graph. First we are going to learn about the cutoff region. What is cutoff region? Look at here. Here the graph is drawn when the IB base current is kept at 0 microampere. Though the base current is 0, some amount of collector current is flowing. the flow of collector current is observed and the graph is drawn. Just below to the curve, just below to the line, this region, this portion is called cutoff region. If you go down, what happens? The collector current, main current, it becomes zero. Therefore, this region is called, what is this? Cutoff region. That is the portion, the region just below to the line IB is equal to 0 is called as cutoff region, because collector current, it becomes 0. Now we are going to learn the second region in the output characteristics graph. The second region in the output characteristics graph is saturation region. Now we have to find out which one is saturation region. Here, when VCE is increased, there will be a corresponding increase in the IC also. Here, when VCE is increased, IC also increases. Since it is obeying Ohm's law, that line OA that represents the ohmic region. Are you clear? After attaining a point, that point is called knee point. After attaining a knee point at a particular knee voltage, the value, IC value, that one becomes constant. That one value becomes constant. This region is called saturation region. How to find out the saturation region? In between this ohmic region, in between this ohmic curve, ohmic region and the origin, here one region is available now. That name of the region is called, what is this? Saturation region. That lies between the knee point, that is in between the knee point, knee voltage and the origin. One region is available. That region is called, what is this? Saturation region. Always the transistor that must be operated beyond the knee voltage. Always transistor must be used, is it clear, only beyond the knee voltage. Now we are going to see the most important region in output characteristics graph. That is nothing but active region of the transistor. Are you clear? So in the central part of the graph is called active region. When the transistor is in the active region, the base emitter junction is forward biased and base and collector junction is reverse biased, and the transistor that can be used for amplifier purposes. To construct the amplifier circuits, the transistor can be used, especially in active region of the transistor alone, that amplification circuits must be used. Are you clear? For current amplification, voltage amplification, and also for power amplification, the transistor can be used in active region. Okay, that is the most important region. Now we are going to learn the next region called breakdown region. Breakdown region means, is clear, if you increase the value of VCE beyond the prescribed value of the VCE, the transistor, that one will get damaged. Are you clear? When VCE is increased and IC also correspondingly increases, and finally it attains a constant value. Let us imagine this is the prescribed value of the VCE by the manufacturer. If you increase the value of VCE greater than the prescribed value, collector current starts increasing. That one will damage the junction of the transistor, and finally avalanche is clear, breakdown will happen. Due to the avalanche breakdown, what will happen? The transistor will get damaged.